So, you may have heard about how the Japanese revolutionized the manufacture of cars by a system called just-in-time manufacturing, where you don't keep parts lying around for months in a warehouse. It's just-in-time delivery is what it's called. Yeah, they save the amount of storage space.
That's what Boeing does, right?
Boeing? Well, now everybody does.
Everybody
Japanese
does.
are, I think, we're getting
Yeah.
to that.
Well, I think the Americans invented it, and then the Japanese stole it.
They stole the idea of thinking.
Harley Davidson is famous for that because
Uh-huh.
Harley Davidson is famous for that because right before they started doing that, they were almost going out of business because they had parts, most of it was falling apart. The parts been around too long.
So anyway, Jim and I have introduced this practice into mathematics. So often, like, people prove a mathematical result, let it sit around for centuries in some warehouse, then we teach a course on it. We decided it's much more efficient if you prove a theorem right before you actually give a talk about it. But the problem with this system is that sometimes the theorem is wrong. And that's the same type of problem that could happen with just-in-time delivery. Right? You're cutting it close. So I was stating what was supposed to be the fundamental theorem of Hecke operators, but it really was like the first attempt at a fundamental theorem of Hecke operators, which is not quite true. So let me state the true part of the theorem, just for the record, and then say a bit about it. So what we had here was just-in-time delivery of pens. So I really black. So let G be a group. I guess it doesn't need to be finite. And let X and Y be finite G sets. Maybe this one. Nope. So well, sorry, this is a stupid way of stating it, but I'm stuck now. So let X, Y. Let's just be the set of morphisms in the category we're calling finite G sets. Thanks. So what is it? So it's the set of isomorphism classes of spans of G sets going from X to Y. So then what we've seen is that this is an end module. So you can think of these things as matrices of sets, and it makes sense to add two of those things by taking the disjoint union of each matrix element, or to multiply it by a number. Take a bunch of copies of that set. So this is actually a finitely generated free end module. If G is finite, now I can use it. And, sorry? I'll mention that in a minute. So, and we have map from this on XY to the vector space of intertwining operators from the permutation representation associated with X. started talking about this theorem over the complex numbers, then I guess we decided it works over all sorts of other fields, maybe even more generally over rings. Let's just do it over some field K. So K to the X is a vector space over the field K. It becomes a representation of the group G, where G just removes the basis elements, ditto for K to the Y. And we can reinterpret these kind of matrices as linear operators, and Jim showed a long time ago that you do get intertwining operators. That's true. There's a bit more to it.
Oh, I'm sorry, did you find that now?
You defined that map,
Last week? Okay, okay.
and I defined it last week.
Yeah.
So you take your span of finite G-sets, turn it into a matrix of natural numbers, where the ij entry is the cardinality of the set of guides that maps down to I and j. You get a matrix of natural numbers. You think of that matrix of natural numbers as a matrix of entries in your field K, because it's a map from the natural numbers into your field K, homomorphism, and so you get your operator, which is an intertwining operator. So we have a map like that, and so a particular one, I'm sketching, this is all stuff I said before. And what we can then do is take this free n module and turn it into a vector space, and tensoring it with K, and so we get a linear map from that to this vector space. The same vector space we had before, the intertwining operators. For any field K. So we get this. We get a linear map this way, K linear map. And what I said last time was that this is an isomorphism. This is one-to-one out. It's not true. As Jim explained, it's just on. So if we just try to rescue my theorem by them changing it slightly as possible, getting something true, then we're left with this. So that's much less exciting sounding, because it's always very exciting to say things are isomorphic, when it's exactly matching something else. It's much less exciting to say that some map is onto. And so one would like to capture the more precise fact that's working behind this somehow. And that more precise fact was the fact that the Hecke operators coming from the invariant atomic relations actually provided a basis of this space. That's when we were talking in terms of relations. But now we're talking in terms of spans. This is not the invariant relations next to Y, it's the invariant spans next to Y. And as Jim pointed out, there are lots of spans, key invariant spans next to Y, that aren't just linear combinations of relations. So there's a lot more in here than I can ponder. So this map is not one-to-one. So there are different ways to try to polish, or not polish, to try to make the statement be both beautiful and say exactly what it means. And the best ways involve actually changing the way you talk about this a fair amount, not just like little tweaks like this. And so that's what Jim was beginning to talk about last time. So what we really have is this two category of G invariant spans right here. G sets, G-invariant spans and morphisms of G-invariant spans. And here I've decategorified it a certain way by looking at isomorphism classes of G-invariant spans. So I decategorified it, and then I critified it and hoped that I'd get exactly the intertwining operators. But it didn't. It didn't quite work. I decategorified it the wrong way. That's the wrong way to make some beautiful statement about Hecke operators. The right way, Jim just began to mention right near the end of his talk last time. The right way involves thinking about spans of groupoids. And I don't think I want to state that right way just now, because to state it nicely involves some extra concepts that I haven't introduced yet. So I'll just take a rain check on that and say, so to state this, to state a better theorem. It's good to introduce a new concept we haven't really talked about much yet, which is spans of groupoids. So that will be that for now. And now I'll go on over to the other topic that I was discussing. And we'll see that there too, we're going to need spans of groupoids to do something nice. So we're getting pushed into this. So we've been talking a lot about spans of sets and spans of G-sets. And a groupoid is a kind of generalization of both of those things. And I'd always been wondering, at what point in this course would I get forced into introducing group spans of groupoids? Because Jim and I are actually very interested in spans of groupoids. That's really what this course is about, this long 2-year course that we're involved in. But I was trying not to just sort of drop them on you from Deus Ex Machina style, but to see where they showed up. And for some stupid reason, I sort of saw where they showed up by backing into them. Oh, that's why I need spans of groupoids. I'm screwing up unless I introduce them. So okay. So I think this other topic, the topic of Pascal's triangle, may be a slightly better way to walk forwards into spans of groupoids, although I'm hoping that Jim may decide next Tuesday to clarify this fundamental theorem of Hecke using spans of groupoids. But anyway, so last time we considered Pascal's triangle. And the way we did it was we looked at a categorified version of Pascal's triangle, where we picked the field F and n choose k sub F means the Grassmannian of k-dimensional subspaces in F to the n. And then we looked at a small portion of Pascal's triangle. Sorry, I just want to draw it exactly the way I've always drawn it. I'm drawing it. So 2 entries directly below in Pascal's triangle. So this is part of the nth row of Pascal's triangle. This is part of the n plus first row.
Yes, k plus 1 k.
What? Yeah,
You usually do k from 0 to
Okay.
order.
Okay, yeah, that makes sense. Okay, since I obviously have no idea what conventions I'm using, so can you look and see if this is this arrow here that we were beginning to discuss is the one called X or the one called Y? Let's see, I think I have my own idea.
No, that's right.
Sorry?
Right.
This
You
is
have
Y?
y on to the left.
Okay. I think all my conventions are maximally bad. but maybe that's all I'll remember. Maybe that's all I'll remember about it. Worst possible thing. So, but of course, so we were trying to describe what kind of processes there are that allow you to somehow relate a k-dimensional subspace of f to the n, and either a k-dimensional subspace of f to the n plus 1, or a k plus 1-dimensional subspace of f to the n plus 1. And these processes, they're not, in general, functions. One way to think of them as spans. So one of these was actually a function. So here, x and y are spans of finite sets. So y is apparently the sort of simpler one. What? You have different notation?
Well, here you have this, and that's not equal to the switch.
No wonder. Let me go back. The last class I just briefly mentioned them at the last minute when I was rushing. Before, I did a whole big fat discussion. So let's get that. So last time, let's just say that was a little glitch. Yeah, I think that's right.
No, just one. No, why?
Sorry?
Which was the glitch last time?
Last time was a glitch. Last time I just mentioned this Pascal triangle.
This was what you did last time. This is the glitch. That's the glitch. You had it right the first time.
Well, why didn't you tell me? What, are you trying to correct me by telling me that I'm doing something right? I thought you would only mention it if I was doing wrong. Okay. Good you are. So y is apparently the simple one. So the point is that if I have a k-dimensional subspace of f to the n, there's an obvious way to think of it as a k-dimensional subspace of f to the n plus 1, just by taking fn and embedding it in f to the n plus 1 in the standard way, using the standard basis. So I could really think of y as a function, but because I can't think of x as a function, I will think of both of them as spans. And so this one, although it's really a function, can be reinterpreted as a span. We did all this where we just used the identity function on this leg of the span. And here, we do something a little bit more interesting. This arrow here, what it does is it takes any subspace of f to the n and extends it over to that same space, but now thought of as sitting inside f to the n plus 1. I'll copy that at the very end of the list of specific embedding of fn plus 1. So that's a span. Okay, so it's a span of sets. Now, what we really like, because we like Hecke operators, is we like spans of G sets for some group design, right? So it'd be nice if we could interpret this as a span of G sets for some group. But what's funny about it? Okay, what's not funny about it? You actually thought it was funny that I said something funny, and I thought it was not funny. That's a good question too. So how can I interpret this as a span of G sets?
Well, you better pick your group G first.
Yeah, all right. I better pick G. So what's G? That's the big question.
GLNF.
It could be GLNF.
And then GLNF plus 1.
Right. So that's what's funny about it, right? GLNF acts naturally on this cross monoid here, but GLN plus 1 acts naturally on this one here. And so there's a slightly schizophrenic thing going on in terms of the choice of groups. You can get over that by using the fact that GLN.
Shouldn't that be n plus 1 or something?
Here?
No, down. Left.
This is not the Pascal triangle. This is the span.
This is span.
Yeah, you guys were also getting confused by that last time. These are actual functions. They're not slashy things.
Do you have any idea how confusing that is when you draw that? Exactly like that.
I mean, you know. It's letter I looks exactly like that letter I, and I don't like it all.
It's a really big warning sign saying, like, these things that look identical are completely unrelated. Because they're really.
I'll just say, these things which look completely identical are completely unrelated, except of course they're extremely related, but they're not the same. Okay? You all got it? Okay. So, yeah, so I never would have thought of getting confused about this, but yeah, you're right, they're both sort of triangly shaped things. So, okay, so with a bunch of branches, things. So this is a picture of Y. This is a picture of the span Y.
Okay.
So that's not Y. The colon is in like so not a mapping. So okay, so but it's awkward. Treated, possible but awkward, treated as a span of G sets. Since GLN F is the group that likes to act on the Gaussian of K-planes and N space, but GLN plus 1 F is the group that likes to act on this other Gaussian N plus 1. Now you may say, wow, come on, that's no big deal. We have a homomorphism from one of those groups to the other. When you have a homomorphism from one group to another, that lets you take one G set, turn it into a set on which some other group acts. So we have this homomorphism, which is the inclusion, but I'm going to call it D for some description. From GLN plus 1. So that lets us get over this thing. But you see, but it's still sort of a little ad hoc or awkward. And
No more awkward than we have studied, right?
right, that, okay. That's just as awkward as this, is how I prefer to think about it. So we're doing something mildly distasteful here about picking a standard way of thinking of Fn to inside Fn plus 1. Of course, there is one, but there's lots of them. And whenever you're making a choice like that, not red flagging it, you're losing some of the symmetry of the situation. So that's right, that's the problem. That's where the problem springs from. And so this isn't such a terribly important reason to get involved in the spans of groupoids. But this is, in fact, one kind of little example of how spans of groupoids can be used to avoid making up your mind which group you're talking about. So we'll use the span of groupoids instead to talk about this stuff. So I'm using this as an excuse to switch my point of view a little bit. So remember, a groupoid is a category where all the morphisms are isomorphisms, or where all morphisms are invertibles. And one way to get lots of groupoids for free is to take any category, you just throw out all the morphisms that aren't isomorphisms, and you're left with some category, which is a groupoid. So any category C has this underlying groupoid, which deserves to have something. It's an important concept, so for some silly reason I just stick a 0 on it. So it's the same objects but only the isomorphs as morphisms. So I think I've been talking a little bit about some of these kind groupoids, I forget how much I've talked about them, but we will in fact be talking a whole lot very soon about the groupoid that we get by taking the category of finite sets and functions and then converting it into a groupoid this way. So you get a groupoid of finite sets and bijections. And the reason why we're going to wind up talking about that so much is because it's equivalent to something else that we've already been talking about. Well, we haven't really already been talking about it, but ingredients of this thing over here we've been talking about a lot. So if you have a groupoid, very much unlike a category, because the only morphisms are isomorphisms. You can never have a morphism between non-isomorphic objects. And so the isomorphism classes of objects will be like these separate blobs. Jim called them components last time. And there can never be a morphism from one of those components to another one. So your groupoid will be a kind of disjoint union of these pieces, these components. You want to show off your friends and say it's a co-product of these components. And those components, because everything in them is isomorphic, become very simple to understand if you just take one representative of each isomorphism class. In other words, take what's called a skeleton of it. So you can always take the category and get an equivalent category where you just take one representative of each isomorphism class. So if I do that, I see that my groupoid is a disjoint union of groupoids, each of which just has one object. And what's a groupoid with one object? It's a group. Right. So after they defined groupoids, they realized that the one object case was interesting. Groups? Yeah. So call them groupoid. So you can take any groupoid and think of it as a disjoint union of groups, and what do you get in this case? That's not group. Co-product, so it's a disjoint union or co-product, which is written upside down product symbol, of groups and band. Yeah, so the natural numbers shows up. The natural numbers is the set of isomorphism classes in index. So that's what index is, your disjoint union. But for each n, you pick your favorite n element set, call it n, just to confuse people, and then it's automorphism, somewhat, and back. So, yeah, so we've been studying a lot about actions of n bang, but now this is a way of studying all of them together in one big structure. Yeah?
But I don't understand what just happened. I don't know if you just snuck something in, because, yeah, I guess you didn't make it clear the process by which we associate a finite set with the group.
So what?
I mean, I guess you did say it. You said you associate two of the group monomorphisms with that finite.
Yeah, it's buried into what I was saying about skeleton, right? So if I want to do it very generally. So I have some groupoid here. I look at a component, so that's a bunch of isomorphic objects. All the objects in some isomorphic class. And then I say that component is equivalent to a skeleton. So how do I create a skeleton? Well, what I do is I take one representative from that isomorphism class, and I only look at the morphisms between those representatives. Well, there's no morphism from this representative to some other representative. So the only morphisms from it to other representatives are morphisms from it to itself. So this component here, this is a groupoid of all n element sets, for example, and all bijections between n-element sets. That big fat thing is equivalent to the skeleton, which is my favorite n-element set, and all the bijections from it to itself. And that's what we call n-bang. Group n-bang.
Where we're thinking of each n-bang as a groupoid with one object.
Right. Right. So we're going to completely think of identify the concept of a group to the concept of a groupoid with one object. We're not going to worry about some kind of notational distinction between those two concepts that you might have. So a one object, so henceforth, right, so a group is a one object groupoid. This is how they should have done. So then you get this theorem that every groupoid is equivalent to a coproduct of groups, one for each isomorphism class. So we get that. Also, we've been looking a lot at finite dimensional vector spaces over a field. That's a category. But if we look at the underlying groupoid of that, we can do the same trick of writing it as a disjoint union of components, one for each isomorphism class. And so what do we get here?
GLN?
Yeah, we get all the GLNs. So again, the isomorphism classes are indexed by integers. Now the dimensions instead of the cardinalities. And then for our favorite n-dimensional vector space, we look at its automorphisms, and that's called GLN. So, yeah.
I don't know if you already said that. It sort of bothers me that you're talking about coproduct, and then you're writing groups, and it sort of suggests notationally that you're going to take the coproduct of a bunch of groups.
No. Yeah. So.
Well, I'd like to have some
that.
sort of, but you didn't. I didn't finish my sentence.
Okay.
I would like, therefore, some sort of declaration on that group name to indicate that you're not just taking the group, but
Right.
somehow looking at it as a one-object groupoid.
Right. So some people are like that. So, and I just said before, I'm not like that. I said I was deliberately not going to introduce any notational declaration on a group. Say, I'm thinking of it as a one-object groupoid. Sometimes that's very important because the category of groupoids is different than the category of groups. And coproduct in the category of groups is what Willie then calls the free product. Coproduct in the category of groupoids is a much simpler thing. We just set the groupoids side by side. We don't have any morphisms going between them. And so here I definitely mean coproduct in the category of groupoids. And so if you're like that, I should stick some little twiddle on this to mean that now I'm thinking it's a groupoid. But I just
Put
don't.
a quarter at the end, that's what we're doing.
Okay, well, that's what you want to do. So-
I just wanted to say that.
Okay, yeah, I mean, you do have to worry about that. You do have to worry about the fact that even though you use the definition, the category of groups and the category of groupoids have very different properties. Co-product behaves very differently. Okay. Product behaves similarly. So, okay, so let's see. So we can switch from thinking about spans of G sets to a new viewpoint, thinking about spans of groupoids. And this will solve this slightly awkward problem that sometimes we have a span, something like a span of G sets, but we haven't quite made up our mind what G is, as in our problematic example. So, roughly speaking, it would go like this. So, if you give me a G set S, there will be some way to turn it into, I'll describe in a minute, some way to turn it into a groupoid, which I will write as S mod G, but it's weakly mod G. I need to explain. So I write some funny symbol for mod, which is different than the usual mod. And then if I have if I'm in this funny situation where I have a G set S and a G prime set S prime, that's the funny situation we're in, and a homomorphism from one group G over to the other, so that's what we have, this homomorphism from GLN to GLN plus 1, so a homomorphism. And the map from my first G set to the second one, which is like a map of G sets, but sort of takes into account the fact that I also have a homomorphism of groups going on. That's what we've got in our example. So what's going on is that we can apply an element of our first group to our first set, and then send it over to living in our other set, and that's the same thing as sending that element over, and then now it doesn't make sense to apply G to it, because now we're in S prime, but we can apply C of G to it. So if you don't notice the distinction between different fonts of Greek letters, it's all C, D, and that's sort of okay, because it's all part of the same package. So this package is what we have in our example, where we have one G set for one group G, some other G set for some other group G, and a map between them that goes along with this inclusion, mechanism inclusion of one group. So that's what we've got in our example. So this big, complicated, awkward thing that we have in our example coming from Pascal's triangle will get turned into just a functor from the groupoid I build out of G and S to the groupoid I build out of G prime and S prime. So it'll become a lot slicker, in other words, to talk about this kind of situation where you're not quite sure which group you want to be using. Something nice. So I want to describe how you do this thing. These tricks. They're not really tricks in a bad sense. They are actually very natural ideas. So by then, you see how it works. You'll be converted to groupoids. You'll never want to think about G sets again. Well, you actually will, but you'll never really need to. You can always think about them as certain groupoids if you like. You can say more about how, but let's start it right now. So given a set S on which group G acts, how to build a groupoid somehow captures a lot about what's going on. First, I think I will illustrate it with an example. Very what? I don't know if that's a good input or not. I always call it the weak quotient. Jim likes to call it the groupoid of elements of something or other. But all of those terminologies sound much more intimidating than the actual idea. So, for example, here's my set S, And suppose I have some group acting on it at symmetries. Well, there is a sort of obvious group acting on this picture symmetry, namely reflection. So let's say D mod 2 is acting on this S. So what does that mean? Well, it means that I can reflect this guy, and it goes over there. And similarly, of course, I can reflect this guy, it goes over there. This guy, if I reflect it, I get itself back. And if you look at what I just drew, I'm starting to draw a groupoid. I'm drawing a bunch of objects and a bunch of morphisms, if you think of it. So what did I do? I took the objects to be the elements of my set S, and I took the morphisms to be, well, something like elements of this group G. Although I only did the case so far for one interesting element of G, non-identity element. These are morphisms coming from the non-identity element of C mod 2. We also had better have morphisms coming from the identity element of C mod 2 if we're going to get a groupoid. Those are much less glamorous, but I'll draw them into. So the identity element of C mod 2 sends everything to itself, so it will give us a little morphism that goes to itself. And so that's the idea. That's how we do it. So in other words, the objects of S with D mod G are the elements of S. The morphisms, what are the morphisms? Tell me what a morphism in this thing. This stuff.
Arrow from S to G.
An arrow from S to G of S. Right, so, and that arrow needs to be labeled by which group element it's coming from. Because sometimes have two different arrows going from to the same thing. So we need to label the arrows both by the object that it starts at and the group element as well. So the sorry? Yeah, so the morphisms are just form the set G cross S. So the morphisms are pairs. G, S. So G comma S goes from S to G of S. So here's S pair G comma S. And you compose, you have to say how to compose them, but it's sort of the obvious way. I guess I'll say it. It's the obvious. So what we're doing, you see, is we're building the group action into the structure that we're studying. It's no longer a set. It's a set with built-in symmetries, arrows. So it's a groupoid. So here's how we compose them. So if I have a morphism G comma S from S to GS, then I might have another morphism. So it can be H comma, well, it has to be H comma GS. It's starting with GS. And so then it takes me over to where? HGS. Careful. It's an action, so I don't need to write parentheses on it. So it's got to get the order right. And so when we compose those two, we better get a morphism from S to HGS. And what's that got to be? Sorry? HG, S. Didn't say the comma. We're trying to annoy you. Yeah, that's right. So that's over. So it's just the obvious thing. So in other words, like, so if I hand you a cube and I tell you you're allowed to rotate this cube, so you have a set of positions of the cube, there's group acting on it, then I'm really handing you a groupoid. I have the objects being all the positions of the cube, and the morphisms being these rotation operations that go from one to the other. So you should not think of this as like a complicated trig. It's supposed to be just a way of thinking about set with built-in symmetry as a groupoid. So that's how that works. Let's do an example. Yeah.
Do you have any potential to how you call if our doesn't matter? Like GS, how many T is not S like GS?
Well, you shouldn't be composing arrows that don't match up.
Yeah, then maybe you just not
Is that what you mean? Composing arrows that are not composable? Yeah, no. Yeah, you only, right, in the category, you only care about composing arrows if the target of one matches the source of the next one.
Maybe I think maybe this question is just too simple, but
Okay, Tom, one minute.
okay, no answer. But what if you have? I'm not gonna ask this.
Go.
I'm worried this is a groupoid at all because why is everything convertible?
Oh, that's not too simple.
And then I just realized why it's convertible. And
Okay,
said that.
well, let's just break down the formula for the inverse. So,
Yeah.
the inverse of GF, it's possible to get confused about this. I can do it.
G inverse.
G inverse GS.
Yeah.
G inverse, it better be G inverse.
G inverse GS.
Oh, right, but it starts not at S now, but at the other end, it's G. So it's possible to screw that up and write S. G inverse S, you don't really get confused.
That's what I was first thinking of.
Yeah.
It
No,
didn't make
yeah.
any sense, and then okay.
Right, yeah. So, but there is an obvious thing. You can check this and see. So we did get a groupoid. I'll let you figure out what the identity is, so that's easy. So, what the identity morphisms are. So let's do an example. What example? Well, the example that we were messing around with in Pascal's triangle. Right, so we have GLN, comma, field F. It acts on the Gauss-Monnian of K-planes in Fn. So there's a great example. That's the one we were actually dealing with. It got us into this trouble in the first place. So we got a groupoid out of that. And I claim that if we figure out what that groupoid is, and massage our description of it a little bit, the groupoid will have a name or a description that's very sensible and sort of not more technical than what we're talking about here, but in some sense less technical and simple. It'll start out seeming technical, perhaps, but we'll massage it until we see it's nothing too complicated. So here's our groupoid. Oh, that was really technical there. So we get this groupoid, but now let's figure out what its objects are and what its morphisms are. And then let's think about other ways to describe it, or to describe equivalent groupoids. So this guy, so the objects, so what are the objects of this groupoid?
K-planes.
K-dimensional subspaces, K-planes. So the K-dimensional guys, B sitting inside. Okay? So then we ask what are the morphisms? Well, I'll ask it this way. What's a morphism? I'll ask you what's a morphism from some particular object to some other particular object, just to make it hard. What's a morphism from B, from that object, to, say, B prime? So what is it? So you could easily tell me what are all the morphisms, just the group cross the set. That's not what I want to know. I want to know what the morphism from B to B prime. It's an invertible.
And then problem is the invertible mass function of Fn that takes me to be right.
Yeah. So it's a guy in GLN who sends this subspace over to that space. So it's an element G ln, which maps being convertible, is 1 and 1 and on the way.
Fully invertible on A1.
Nope.
It's in GLN.
Think about how the definition goes, right? So the morphisms in our groupoid are really just coming from the elements of the group, right? Thinking over here off the stage, right? So the objects are the guys in here. Morphisms are a pair consisting of a group element in here and a guy in here. So a morphism is really a pair consisting of a guy G and a guy B. It goes from B over to G. But it's, okay, so that sounds complicated perhaps, but it's not really supposed to be complicated. An object is just this kind of thing, a plane. Morphism is just a linear transformation that carries one plane over to another plane. Same dimension, of course. But there's something even easier way to describe what's going on here. In fact, this groupoid is equivalent to something that sort of takes less time to say. One object set. A one object set? What
I mean,
you mean a one element set or a one object?
I mean, I'm sorry, yeah.
groupoid?
One object.
This is not a one object groupoid already, right? It has lots of objects.
It's skeleton.
It's equivalent to a group.
They're all isomorphic to each other.
Yeah.
It's true.
Yeah.
Oh, so you're trying to do that. No, that's not at all what I was thinking of doing. So you were thinking of replacing this groupoid by a skeleton.
I'm just saying that's transitive.
And that will be-
any subspace to any other subspace, at least one invertible transformation.
Yeah. Right. I don't want to even, I don't want to guide us down that path, although it's a very tempting path. So let that remain the road not taken. Yeah. Let's take another road. So,
And it will make all the difference.
is that how the phone goes? Yeah, it'll make all the difference. Make a lot of difference to me. So what you were trying to do is sort of whittle down this groupoid by not considering so many different subspaces of Fn, because they're all isomorphic. What my idea was to go the other direction, to whittle up. That's not really worth it. De-whittle the groupoid by saying, hey, sure, we can talk about subspaces of Fn, but there are lots of other n-dimensional vector spaces that we can use as well. They're all isomorphic, so it shouldn't matter too much if we puff up this groupoid a little bit. I'm going the other direction. You're trying to think of skeleton. I'm trying to say, throw more stuff in, but just stuff that's isomorphic to what you have already, so it doesn't really hurt. And that will allow us to not be talking about F at the end, as God's favorite n-dimensional vector space, but talk about all the n-dimensional vector spaces. So can you say it? Can you say which groupoid I'm after?
Vector space is a normal. Oh, n-dimensional.
Well, what's an object? An object will be something. So an object won't just be a k-dimensional subspace of F through n. That's very special. An object will be
K-dimensional subspace of an n-dimensional space?
of an n-dimensional space.
So that's a flag?
It's a particular type of flag. Yeah, that's right. A very particular type of flag.
NDA flag.
So yeah. Right. I know. Some particular Young diagram that has n boxes and k boxes on the first row. Right? So, right. So it's equivalent to the groupoid. I'll say it slowly at first here, where the objects are n-dimensional vector spaces I'll just remind you over the field F, equipped with k-dimensional subspaces. Equipped with a k, each one of course is equipped with one. It's a k-dimensional subspace. Okay. Okay, that's what the objects are. Hopefully, if you say what the morphisms are correctly, all the morphisms, every one of these objects will be isomorphically just one of these. That we mentioned before. And so a morph, let's see, I should introduce some names. Well, I'll do it now. So a morphism. So what are the morphisms going to be? So a morphism is going to be something going from some n-dimensional vector space to this k-dimensional subspace. So I'll just write that to me. My n-dimensional vector space W and its k-dimensional subspace. So a morphism from that thing. Yeah, but I have some other line in mind for when I get serious. So we're going to get more complicated flags coming in that are longer, that have more terms. So definitely, this is like the homemade notation, not the ultimate notation when we go do this stuff on an industrial scale. So a morphism from one of these guys to another one is what? Ooh, okay, that sounds more slick than what I would have said, but fine. So, I think I know what you mean. So the idea, I guess I'll just read your mind. So we've got V included into W, and we've got V prime included into W prime. What's the morphism from one of these guys to another?
What's the right-hand arrow?
First, the right-hand arrow. So some linear map here. What kind of linear map? Invertible. Wait, we're aiming for a groupoid. Right? So we've got to have an invertible map from W to W prime. And then...
What is that thing? Is that
what's
iota?
No, it's isomorphism.
Oh, okay.
You gotta look at it like this.
Tilde on the mid-93.
Yeah, you can write it like this. I never know.
Okay.
So, some particular one. And what about, that's not a square yet, so what next?
You just restrict that thing to B.
Yeah, it has to have the property that when you restrict it to D, it maps into D prime. So we don't really get to pick this, this restriction of this one. So this is really, all our F is that. So in other words, i.e. isomorphism F going from W to W prime, such that F of the little subspace D is the subspace. So what we're doing here is we're taking our previous groupoid that we talked about and generalizing it by not requiring that the big subspace be at the end anymore. So it's any old n-dimensional range. So instead of this guy being in GLN, it's just any old invertible map now. But this big new groupoid is equivalent to the littler one because every object in the big groupoid is isomorphic to one. So the little one is a subgroupoid of the big one, and it has the property that every object in the big one is isomorphic to one in the little one, and that implies that they're equivalent. So general about that. So this is equivalent to this, but in fact, there's like a quick way to say what this groupoid is. So often when you name a groupoid, you just name it by its object. And you expect that the person listening to you has enough brains to know what an isomorphism between those objects is. Sometimes you could be wrong, either because they're stupid or because they're like two different possible concepts of isomorphism. But if I say like the groupoid of finite sets, you're supposed to know that I mean bijection. So in that style, so this is the groupoid, something like the groupoid of NK flags. Maybe I was going to not be quite so sophisticated about it, but I just say something like, this is the groupoid of n-dimensional vector spaces equipped with a k-dimensional subspace. So the idea is very often you build up. So you're supposed to know what the groupoid of n-dimensional vector spaces is. Morphisms are the invertible linear transformations. Now we're just saying, okay, take those guys and equip them with a little extra structure, and we demand that the morphisms preserve that extra structure. So that'd be just like, if you're supposed to know what the groupoid of finite sets is, then I could talk about the groupoid of two-colored finite sets. And you're just supposed to know that the morphisms there are bijections to preserve the color. So this is very much like that, extremely like that. Extremely like that, because we can do the same kind of thing at the q=1 case, where our flags are dealing not with vector spaces, but with sets. And then this kind of flag we're talking about is just two colors. There's the guys that are in the subset, and the guys that are out. So let's just be a little more general here. We have this notion of a categorified multinomial coefficient. So this thing here, right, was the set of flags in subspaces nested one inside the next, total of k of them, where the biggest one was Fn, the smallest one was zero-dimensional subspace, and the dimensions of the quotients are these numbers, n1 for k. So it's a set of So this is a generalization of what we just did. GLN acts on this set of flags. So we could create a groupoid by this construction where we let the objects be these flags, the morphisms be guys in GLN that map one flag over to another flag. And this groupoid here is again equivalent to one, where we do the same puffing up kind of construction. We don't just think about flags in Fn, we think about flags in all the n-dimensional vector spaces. And so this is equivalent to the groupoid of what? So we're gonna, I'm taking all the work that I just did in the previous example and speeding it up. The group of D flags, that's not quite the best way to say it. I don't mind you saying D flags. In fact, let's call these things not just flags, but let's call them D flags. So D here is our Young diagram, which has uncombed Young diagram, which has, right, some Young diagram that has ni boxes, sorry, what? Ni boxes in the ith row. So this particular kind of flag is called a D flag. So I didn't need to write all this stuff, but I just said it's D flag.
You want to say the groupoid of n-dimensional vector space equipped with a D flag?
Yeah, I could say that's more like what I wanted to say. I didn't want to say, oh, D flag. That's like having D flag wants to live in somewhere. It's very scared. It doesn't know. Maybe it does know where it is. But it just sounds a little scary. So I think groupoid of two colorings. I just like to say groupoid of two color finite sets. So you could say the groupoid of vector spaces You can say of n-dimensional vector space is equipped with a D flag, but then you could get cutesy and say, well, there's no other kind of vector space that could be equipped with a D flag, except an n-dimensional one, right? Because the Young diagram tells you the dimension of the vector space. So let's just be cutesy like that. Groupoid of vector spaces. I guess we should say over F. Equipped with a D flag. Or I guess if you get tired of saying this, as we undoubtedly will, because we're going to talk about this a lot, we could say D flags vector spaces.
D flags and vector.
Yeah, so we might even make up some notation for this, and I think it's about time to do that. So I had before made up a notation for this set of D flags on Fn, and I called this thing D of Fn. That was another interesting set of D flags on this particular n-dimensional vector space. And that notation is nice because you could also put it in an element set in there. So let's try to do something like that. Yeah. So I was fighting with myself, trying to think of like the best notation. And so you're suggesting I should do something very similar here to what I did over here. So it should be D of something. And maybe it should be of vect F. Maybe it should be in vect F, but that we don't really need to worry about that because the vector space needs to be finite dimensional to allow a D flag. Yeah, let's try to use that kind of notation. Right, okay. So these are some very interesting groupoids, and I hope you notice what has happened to our humble binomial coefficients, or more generally multinomial coefficients. But let me just do the example of binomial coefficients, right? So when you walked into this class at the beginning, we were supposed to have known what this meant, or I think you knew what it meant, and it was supposed to just be a lowly natural number. And then we said, come on, don't think of it as a natural number, think of it as the set of k-dimensional, k-element subsets of your favorite element set. So we said, let's promote it by some mysterious process of categorification. It's promoted to a finite set. This is a mysterious error, right? Because, as Jim explained, categorification is not exactly a systematic process, except in certain limited contexts. And then we also said, well, okay, for extra fun, we can cutiform it. So now it's not just a natural number, it's a polynomial. And then we said, well, but we should categorify that too. In fact, we categorified it first, really, because Q factorial is really the number of k-dimensional subspaces of F to the n. So we got this set of this Grassmannian of k planes in n space. I never said exactly what it was. I said it could be variety, motives. Maybe now I'll be lowbrow and say, well, at least it's a set. You certainly know there's a set of them. Probably better. Grassmannian is much better than mere set, but I'll say that. No? And now what's going on is, you see I'm going one step further. I'm saying, okay, we've got this set of k-planes in n space, but it's more than just a set, really. It's really a groupoid, because they're not just these k-planes, they're also these symmetries, these guys in GLN that take one k-plane to another. Or more generally, a near transformation from one n-dimensional vector space to another that carry a k-plane in one to a k-plane in the other. So now we have this even fancier thing, which deserves some even more glorified title. But it's still just sort of a variant on the same idea. And now it's a groupoid. what should I call it now? If I'm trying to use binomial coefficient notation.
Sub-zero.
Sub-zero? We never had a category. This wasn't a category, so we can't just hit it with a sub-zero and turn it into a groupoid. Sub-zero, you do the category. I was just thinking of something silly like this, a vect. I was just trying to copy what Apurva did, right? So Apurva said, once upon a time, you knew what a d-flag on a specific n-dimensional vector space is. Now, we know about the groupoid of vector spaces with a d-flag. And this is a special case of that. Once you knew what a k-plane in your favorite n-dimensional vector space is, now you know about the groupoid of k-planes in n-dimensional vector spaces. So it's, this notation is redundant. We could also think of this as d of vector m for some particular Young diagram d. But anyway, just trying to get a patent on as many forms of notation as possible so I can collect royalties when people actually start using this math to do something. So, and similarly here, you could do something like this. Set. That would also be important. What is this groupoid exactly? What is
Any set of n objects with specified set of k, any set of n points with specified set of k points.
That's an object in this groupoid.
With via bijections preserving this inclusion. This flat.
Yeah, it's a what? So these are d-flagged.
It's d of set.
Right, d-flagged finite sets where our Young diagram D is one that says that k of our elements are in the finite set and the rest of them are not in. That's the kind of Young diagram that you use to describe Gauss lines. So we can call out this thing D of set for this particular type of D, whereas this guy here is what we just called D of set. Anyway, I'm trying to introduce some notations that I might find confusing, but I'm also trying to point out that categorified things once, and now we're categorifying them again. And so somehow that's something pretty natural to do in this game. So let me just leave off by saying what I've got to tell you about next. It's quite easy actually, but I need to tell you about it. So next, so how the morphisms work, that is how when you have a function from one set to another, a homomorphism from one group to another, and so on, where the first set is acted on by the first group, the second set is acted on by the second group, and that equation holds. So how this kind of thing, we want to see how this thing gives a functor from our first groupoid over to our second groupoid. And it's supposed to be a follow your nose hypothesis. It's supposed to be an obvious thing. So if you have some set with symmetries and another set with symmetries, and a way to turn the elements of the first into elements of the second, a way to turn the symmetries of the first into the symmetries of the second, it's compatible with composition. Something, yeah. So then we should get a way to get it from this way. And so thus, finally, in particular, a span of G sets, which is a special case of a bunch of sets with group actions on them, that would give a span of groupoids. an honest span of G-sets will give a span of groupoids, but so will these sort of weirdo spans of G-sets, where different groups are acting on different guys in the span. So all the stuff we've been talking about, all these spans of sets, spans of G-sets, will fit into this framework of spans of groupoids. And so the program called groupoidification, which is what we're really aiming at in this long-winded seminar, sorry to get around to it, is the program of taking math that's done using linear algebra, vector spaces and linear operators, replacing it by math where you work with groupoids and spans of groupoids. We've been climbing our way up to that slowly by saying things like Hecke operators, invariant relation between G-sets, you get a linear operator. But what's really going on is if you have a span of groupoids, you get a linear operator. That's a generalization of a invariant relation between G-sets. So I think what I'll probably do is that the next quarter I'll maybe just begin sort of ab initio, just describing stuff you do with spans of groupoids. And so you can say that what part of this quarter's purpose was to get you to care about that subject. So what we're going to do is we're going to study spans of groupoids, but we're not just going to study them in abstract. We're going to be studying them very much focused on the examples that we've been talking about, groupoids of D-flag vector spaces and D-flag finite sets. And one of our goals is to categorify a certain hunk of the theory of quantum groups, which I've already indicated vaguely how it's supposed to go. So you can use groupoidification to try to categorify or groupoidify the theory of quantum groups.
We see this quarter, what about this week?
Next week, we'll just twiddle our thumbs and wait for next quarter to start. The next quarter, I've made enough mistakes that we'll easily be able to spend next week and the week thereafter, I guess, cleaning up the mistakes.
How many more classes are there?
So there's next week, next week, Tuesday, Thursday, and the week after that. So I think Jim will go next Tuesday, maybe, before you completely forget what you just about to say. Hanging end of his last talk. Okay.